Most times when people think about squeezing, they are not necessarily thinking about calculus. Maybe you're thinking about squeezing a pimple. That's kind of disgusting. Or Squeeze, the really obscure 1980s band. The only song that I can think of that they sang was Tempted. Anybody who knows another Squeeze song, I would greatly appreciate you putting that in the comments here. So the Squeeze theorem is this kind of random, obscure theorem that appears in a lot of calculus books. It's in the list of required topics for AP Calculus, but there's not a lot of questions out there about the Squeeze theorem, and so sometimes you wonder why we're even studying this. The main reason that we study the Squeeze theorem is to provide a little bit of justification for these two limits here. The limit as x approaches 0 of the sine of x over x, and the limit as x approaches 0 of 1 minus cosine of x over x. These are two limits that if you look at the graphs, they seem like they make pretty good logical sense. The Squeeze theorem gives us a little bit stronger justification of why these work. There are definitely other ways to prove that these limits are true, but Squeeze theorem is a nice, convenient, quick way to get around this. So what exactly is the Squeeze theorem? The Squeeze theorem basically says if you have two functions out there that are trapping a third function in between them, that third function is always in between two functions, g of x and h of x. And the two functions, g of x and h of x, usually end up with a common meeting point that f of x also goes through. So we can say that the limit as x approaches a of g of x, if it equals L, and the limit as x approaches a of h of x also equals L, then that one that's in between them has to also have a limit of L. And so the trick then would be to find two functions that bound the function that you're concerned about on either side, and then they also meet at a particular point. So there's a lot that has to happen in order to make this work. So we're going to take a look at what this looks like for sine of x over x and 1 minus cosine of x over x. Here's what this Squeeze theorem looks like in action for f of x equals sine of x over x. Remember here, we're looking for the limit as x approaches 0. And if we look on the graph, I mean, it seems pretty obvious here that the limit would be 1, but again, we want to have a little bit stronger justification. So we find two functions here, one of which is cosine of x. And we find another function here, which is just h of x equals 1. And if you notice, as we zoom in here on this small piece of the graph, the red function, f of x, is always trapped between g of x and h of x. And the limit of the cosine of x as x approaches 0 is going to be 1, because cosine of 0 is 1. And the limit as h of x, the limit of h of x as x approaches 0 is also going to be 1, because it's just always 1. So they're squeezing or sandwiching in this red function here. And so by that logic in the Squeeze theorem, f of x must have a limit of 1 as x approaches 0. Now, if we do this same kind of process for 1 minus cosine of x over x, now that function is not trapped between the two that we have, so we need two other functions. This time we're going to go with 0 and x. And again, you can see that the red graph is trapped between the green and the blue here, and then it reverses, but it's still trapped between the two of them on the other side of 0. Again, the limit as x approaches 0 of g of x is 0, because it's always 0. And the limit as x approaches 0 of h of x is 0, because at 0 it's equal to 0. So f of x is trapped between the two, and so the limit here is going to be 0. So this is how the Squeeze theorem works. It's a visual example here of how the red function in both cases was trapped between the green and the blue. And they all ended up sharing a common point, and so we could look at the limit at that particular point. What kind of question might you see when we're talking about the Squeeze theorem? You could have something that is really set up nicely for you, a real contrived kind of problem here. F of x is less than or equal to g of x and greater than or equal to h of x for all x. What is the limit of f of x as x approaches 2? And if you notice here, when you graph g of x and h of x, you see that they are both parabolas and they both have a vertex at 2, 5. You could also find that out if you didn't have a graph just by taking 2 and putting it in for x in both g of x and h of x. You'd find that the output is 5 for each of them. By the squeeze theorem, if f of x is always in between these two, you know that at 2, the only value that it can possibly take on is going to be 5. And therefore, the limit as x approaches 2 of f of x has to be 5. So when you see a squeeze theorem problem, chances are you're going to have two graphs that meet up at a certain point. And the point where they meet up is also where you're going to be finding the limit of the function in question here, so the f of x.